Okay. I was worried I was gonna have to do the class without you. All right, and the math professor is on the air. Since Marcy's here, we're gonna actually do the problems. And where is,
Repeating that key, followed by pound. Enter your participant ID, followed by pound. Otherwise, just press pound to continue. You are in the meeting now. You are the first participant. Please stand by.
very kind of you to offer me that. Okay, now, would you like for me to go through a manufacturing cost problem, or are you ready for new and improved material?
The manufacturing cost problem, is that from chapter 2?
Be from chapter 3.
Chapter 3. Yeah. Doesn't hurt to go through it again.
All right. You realize we haven't done a manufacturing cost problem yet.
And we shall do it today.
Okay, well. Then let us begin the beginning. Now the problem that we have is that all these problems are so different from each other.
Oh, I thought you said it. I thought you were gonna say they were so long.
Well, we'll find out. All right, so let me pull up. All right, I don't know what that. And we're on the computer, but man, I tell you, this triple mode of offering classes is just so exciting. I can't believe it. All right, so here we are. Now, finally, this problem, this is on all three. This is going to be problem 3-31. Oh. That's not a 3 though, that's a hashtag, all right. Enlarge this so that it can be seen. All right, why aren't you enlarging? All right, problem 3.31. All right, well, luckily this is another one of our problems that requires a requires us to build a table. Okay, I'm going already. Oh, what a rush.
This is T,
All right, so we have operation. We have our time of setup, and that's in hours. We have our time of handling, which is in,
minute per piece? Is that what that means?
yeah, minutes per piece. We have our time of operation in minutes per piece. We have our tool handling time. And that is in minutes per piece. And time of our non-operation time in hours. Our cost of operation in dollars per hour. And our cost of tooling, also in dollars per hour. Oh, wait, not $4 per hour, but dollars per hour. All right. So operation one is 2.5 hours for setup. It's 0.25 for handling, 1.25 for operation time, 0 time for tooling, 10 hours non-operational, $32.88 per hour for cost of operation, 0 for then operation 2, 1.3 hours, 0.22 minutes per piece, 2.5 minutes per piece, 0.25 minutes per piece, 10 hours, non-operation time, 65.50, and 0.22 for cost of tooling per hour. Per hour? Oh, no. Cost of tooling is per piece, excuse me. All right, I thought that was kind of weird. All right, third operation, 4.1 hours setup time, 0.3 for handling, 1.75 for operation 0, 10, 48.25 and 0 for. Did you already do all of these and you're just listening to me drone on?
Yeah, just listening.
0.85, 0.1, 10, 72.15, 0.16, 5, 1.4, 0.18, 1.67, 0, 10, 45.500. Oh, finally, last one, 0.8, 0.33, 0.95, 0.15, 10, 29, oops, 29.75, and 0.18. Yay! All right, what else do we know? Cost of material equals 5.85. Ah, there we go. The batch quantity equals 40.
What does that see? What?
I'm sorry?
Can you move the cursor, please? Oh, material, okay. Cost of material.
All right, so, wow, all right. So, I'm actually going to take these and move them one below. And these guys, I'm going to go ahead and move over here. All right, so it looks to me like we have to figure out the cost of the cost per batch, and that strikes me as we have to first figure out the time per batch. Feel free to interrupt and correct me here. All right, so let's make some assumptions. I assume our setup is for one batch. Our handling time we're supposed to figure out the cost for this part. Oh, boy. All right. So the time for a batch, or wait, no, we can figure it out as time for a piece. Yeah, that's a ticket. All right, so the time for a piece is going to be equal for operation 1 to left parenthesis, 2.5 hours times 60 minutes per hour divided by our batch size.
Divided by what batch size?
The batch size of 40, right down here.
Okay, got it.
All right, plus our handling time per piece, plus operation time for piece, plus, oh, actually, that's everything. All right. Now I'm going to put parentheses around all of that and divide by 60 to get the hours per piece. All right. Let's keep in mind this is.
I get a different number, didn't
Okay. All right, so it's setup time times 60 to get the number of minutes divided by batch size, which is 40, right?
That times 60, yes. Okay, divided by the.
Now-
I think I know what I did. So you got here. And then that one goes that off. Got it.
Okay. Now, the question is, should we put in the non-operation time also? To decide that, let's do the time per piece in hours. And in fact, let's do that as time per batch. All right, so that would be equal to our time per piece times 60 times 60.
For hour, that'd be 24? Or no, or is it be broken down?
Let's do it times batch size. All right. I say, let's go back here and do, here where it says, time of setup, put another left parenthesis and add our non-operation time and do a close parenthesis there. All right, so that time is actually still in minutes, and there and we would divide by 60 to get hours, which not a lot of hours there. All right, so cost of operation per batch is going to be equal to 32.88 times the number of hours. All right, so equals left parenthesis, setup time plus non-operation time, close parentheses, times 60 plus 0.22 for handling plus 2.5 for operating plus 0.25 for tool handling time. Right parenthesis, times 40, right parenthesis again. Oh wait, no, it's supposed to be time per piece. Where am I going wrong here? Oh, okay. But wait a minute, divided by 60. All right, let's do it this way. All right, equals, let's go 2 left parentheses, time of setup plus time non-operation times 60. I need to put it, all right, there. Divided by 40 would be the time for setup and non-operation time for a single piece. Okay. All right. Then, right parenthesis plus our time of handling plus our time of operation plus
Tool time?
yes, you're right. Tool time. It's just way too easy to get, all right. And another right, and that would be our time per piece in minutes. All right, so equals our time per piece in minutes divided by 60 minutes per hour times our units per batch. Okay, so that would give us, oh, yes, you're right, sorry, all right, there you go. All right, let's see how, all right, here we've got to divide by 40, and here we do not divide by 60. Oh, not to mention, we don't divide, we add here, all right. All right, that's still wrong, but righter than it was. All right, setup time, non-operation time. Oh, why is B12 here? Oh, okay, that was right before. Plus C4 and D4. Okay, but this can't possibly be right. Oh, that's because we need here to go divide by our 40. And a all right, what is C5, D, and E, but all right, this number can't possibly be right up here though, because our time of operation is 125, and we're saying it's only 0.3375 minutes to to do the piece, to make the piece. Man, I'm glad I'm not figuring this out by hand. All right, let's just start over there. Equals. All right, first of all, we got to figure out how much contribution each our setup and our non-operation time is. And we want that to be in minutes and not hours. And divide that by the batch size so that we get per unit. Then we are going to add our time of handling and our time of operation. All right, now that looks more like what I was expecting. All right, so the time for a batch in hours, but the cost per batch, we left out the cost of materials. So that's plus 5.58 for the cost of material times our batch size.
You said add the what again? Cost of material? And then what else?
Okay, over here,
Yeah.
all right, so
that's
it's,
cost material, like that, and then B12, which is the 40, okay.
right, so it's the cost of operation per hour times the time for a batch in hours plus the cost of material times the batch size. Only put the batch size in once. All right. All right, so this is going to be equal to our time per part times our batch size divided by 60. And our cost of operations by per batch is going to be equal to our time of batches in hours times our cost in dollars per hour per operation for this operation, plus left parenthesis, we have a cost of tooling per piece plus our cost of material, wait a minute, cost of material per piece is already figured in here. We don't figure it in everywhere. So cost of tooling times batch size, Bob's your uncle, right parenthesis. All right, we'll see if I can get it right on the first pass this time. Equals left parenthesis, the time of setup plus the time of non-operations, right parenthesis, times 60 divided by our batch size of 40 plus time of handling plus time of operation. There's no time of tooling. All right, so 23.2 minutes per piece on this operation, which means equals 23.2 times batch size divided by 1 hour per 60 minutes. There's no tooling cost, so that's equal to our hours, 15.4667 times 48 plus 25, 0.25. All right, equals our setup time plus our non-operation time, close parenthesis, times 60 minutes divided by batch size, plus our time of handling, plus time of operation, plus time of changing tools, which means that our 18.75 minutes times our batch size divided by, or times 1 hour per 60 minutes, which ends up being divided by 60. Our cost is going to be equal to our time in hours for batches times the 72.15 plus 0.16 times 40 pieces in a batch.
So plus the 0.16 times, did you say 40? The batch size? What you said?
The 0.16 is per piece, right? That's cost in tooling per piece. So yes, 0.16 times 40. All right, we're heaving into sight of the home stretch here. All right, so first we add our setup time and our non-operation time, right parenthesis. That's times 60 divided by 40 plus our time of handling plus our time of operation. And that's all of that. So then we convert that to the time for a batch in hours. So that's equal to 18.95 times a batch of 40 divided by 60 minutes per hour. And then the cost of operation per batch is equal to 12.6333 times the cost per hour, 45.5, and I know I'm looking for something else. Oh, there's no tool cost time.
Yeah, once the quote comes back.
Okay, equals left parenthesis, time of setup plus time of non-operation times 60 divided by batch size plus time of handling plus time of operation plus
No,
time
it wasn't.
of changing tools.
So I can start on the
And that's going to be equal to our time per piece in minutes times our batch size divided by 60 minutes per hour and equals our time for the batch in hours times our cost of operation in dollars per hour plus the cost dollars per piece times batch size for the tools. All right, so equals summation from operation 1 to 6 This is what we're looking for. I wish I'd cheated and had the instructor's manual here with me. All right, so it looks like it's $4,142.74. Did you get that? He said, Ray?
Yes, it was for cell culture, and then the other one in order was
And yet the deponent saith not. Are you anywhere in the vicinity?
I'm checking my numbers.
Not if you're within $500.
What was your question again, Dr. Palmer? Yes, it's supposed to be, every time we get it empty, we're supposed to call it in and then come out. The whole bottle, fire bottle. Tank.
Can you click on that, the cost of operation, the second one down? Yeah.
Alright.
2.5.
All right, so it's the total batch time in hours. Times the cost of operation in dollars per hour. Plus the cost of the tool in dollars per piece times the number of pieces or the batch size.
Okay, I see where we went wrong. Can you click on the total of batch per hour? At 1328. Can you click on that so I can look at that cell real quick? 'Cause I got
I'm sorry, can I click on
that cell.
that valve?
That cell right there that you're on, right? I just need to look at my numbers wrong on that. Okay, so
All right, so it's the pieces in minutes times the batch size divided by 60.
okay. We'll figure it out.
Okay, I'm starting to believe though, that they actually want to know the cost for one part and not the not the cost for the entire batch. All right, so let's do that two ways. Here, I'll divide the 4142.74 by the batch size, and I will insert another column, which will be cost per part.
And, yeah, we discussed more on it. Find out.
All right, so if we have the total time for a piece, that's Camille. Have you not had a chance to see him before? We can introduce you in a minute. Yeah, that's easy. All right, so the cost per piece, here, I'll put it,
Genetics.
right.
One.
Now,
Corn.
that's gonna become the time in minutes divided by 60 to make it in hours, times the cost in dollars per hour. Okay, so that's gonna be $11.10, more or less. Right, and then we can do the same thing, equals our time in minutes divided by 60 minutes per hour times the cost per hour, but in this case, we have to add 22 cents per piece.
The census skill that they have is, it's there, but.
And of course, from there, I could cheat and just pull down the formula.
Oh, and that's in dollars, right?
Yeah, those are all in dollars.
Okay.
Okay, but you understand why here we have to add the cost in tooling per piece. Where here, there's no cost in tooling per piece. Okay, the way you're staring makes me think maybe you're not thinking in terms of that. Right, so our time per piece in minutes, we have to divide by 60 minutes per hour, and then times our hourly rate, and add our cost in dollars per piece to get our final answer.
No.
Okay, I'm getting the feeling you didn't get that.
Oh, no, I got it the first time.
Oh, well, You know, you could have said, all right, Harry, enough already, I got it.
We only have two.
Okay, and of course, since everything is across the board, right, all I did was just pull the formula down to get these other guys. Because it doesn't matter if these zeros get added in to the subsequent formulas. I only couldn't have done it from here because I didn't add in cost of tooling. But I could have done that.
Well, like he says.
You still got the same answer. Right, which means equals so there you go, $97.72 for the part. Now, of course, that's just the cost. We would add a markup when we sold it. Now, we are not doing super high mathematics on any of this, right? It's mostly a matter of making sure we're very careful that we, that our numbers are added, multiplied, subtracted, divided correctly. All right, so we're gonna stop sharing that. And then we're gonna start sharing. All right, so you may remember that we did chapter 4, then went back to chapter 2 and 3 problems, and now we're on chapter 5. I'm hoping you remember that.
Nope, I don't remember that. So chapter 5.
I have the utmost confidence that you will remember it in the fullness of time. All right. So here we're going to talk about control systems. So there's process industries versus discrete manufacturing. We've talked a little about that. Continuous versus discrete control, and computer process control. And I'm really worried about doing this part that Camille will come out and say, "You're wrong, you're telling it wrong." All right, so industrial control is the automatic regulation of unit operations and their associated equipment, as well as the integration and coordination of the unit operations into the larger production system. Unit operation, we're usually talking about a manufacturing operation, but it can also apply to material handling and other equipment that is auxiliary to a manufacturing process. All right, so in process industries, our operations are tend to be continuous, right? So we have some amount of something. It's oil, it's gas, it's metal we're making into powder or whatever. Whereas in production operations, we are looking to discrete manufacturing industries, excuse me. We perform operations on a quantity of materials, and we're making individual parts or product units. Right, so we can have a half a gallon of gasoline that we made, but we can't have half a part that we made. Or half a blender, half a car. All right, so in these unit operations in process industries, refineries and chemical reactions, comminution, boy, I'm not even sure what they mean by that. Chemical vapor deposition, distillation, mixing and blending of ingredients, separation of ingredients, some what we would consider process operations, we would actually end up doing in a batch, right? Like when they make cooked pudding cups, they don't, it's not a continuous, you know, we're continuously feeding in chocolate in one place and gelatin and other stuff in other places, and we just continuously are producing pudding. No, that would be more of a batch operation. So it would almost, it's kind of halfway between process and discrete manufacturing. Right, it does, the pudding cups do come out in individual units, or depending on the size operation we're running, when we buy it, we may get it in giant cans, number 10 cans or something. On the other hand, discrete manufacturing industries, casting, forging, extrusion, machining, plastic molding, sheet metal stamping. Actually, the way they're describing this, they would put making pudding in there also. Because when we're doing casting, ordinarily we cast a whole batch of things at once. It's not that we heat up a tiny bit of metal and then we pour it in to cast one little thing. I mean, unless we're talking some kind of a job shop operation or maybe jewelry making, something like that, very small scale, very craft shop kind of thing. Ordinarily, casting, we would be talking about, we heat up a batch of metal, we have a bunch of molds ready to go, and we pour into those. All right, I'm sure you've never heard of variables or parameters before.
Nope.
So variables are the outputs of the process. I would say variables are, can also describe inputs of the process. They're saying, though, that parameters are inputs to the process. So, okay, that's how you want to divide the world up. When we talk about continuous variables and parameters, they're not ordinarily interrupted, right? If you go to a refinery, it is, there's constantly flow through the whole system. In fact, shutting it down is usually a long process, and turning it back on then becomes a long process too. So when we're talking continuous, things like a refinery, the paper mill, if you remember going through that. Right, so in a continuous process, we can think of that as being, in some ways, an analog operation, right? You can get 3/4 of a gallon of gasoline, where 3/4 of a product, very rare. So we don't have that discrete set of values that we have in discrete variables and parameters that can only take on certain values, and usually those values are whole numbers, right? One blender, one car, one can opener. Now, our discrete variables and parameters, some of them will be binary. In that case, we've only got two values they can be. They can be on or off, 0 or 1. So if it's other than binary, it can take on more values, but again, not an infinite number of values, such as a continuous process might be able to do. And then pulse data, well, pulses can be counted. I think that's kind of important. All right, so here we have a graphic illustration, a continuous analog variable, right? Anywhere along this curve, it might be any value. Whereas the discrete variable, if it's other than binary, usually it's, again, a whole number. But a discrete binary, again, is going to be 0 or 1, is all you're going to have. Now, you can have a discrete number system where it's not a whole number. For example, my scale at home. My scale only can give discrete values, but it will either end up being whole pounds or a whole number and a half, right? It measures by halves. Why? I don't know. I would be just as happy if it didn't tell me 241 and a half, it just told me 241. All right, so our controls can also fall into the continuous control, where our variables and parameters are continuous and can take on any value between two endpoints, or discrete control, where all the variables and parameters are discrete, and a lot of times in controls, they're going to be binary. So in continuous control, usually we're trying to maintain value of an output variable or even an input variable at a certain desired level. Right? We have quality control.
No, I don't think I've got, no, not yet.
Okay, too bad. I was about to bring in an example from that. All right, so in continuous control, our parameters and our variables are continuous. Similar to a feedback control system. But in continuous processes, we usually have multiple feedback loops, right? It's not just we're pouring oil in one end of the refinery and we're getting gas out the other end, and those are the only two things that we're measuring. No, we're measuring all kinds of things. The cracking units, we're measuring the temperature at various levels, the reheater, the boilers, whatever. Examples, control of the output of a chemical reaction that depends on temperature, pressure, etc. Control of the position of a cutting tool relative to our workpiece in a CNC machine tool. Right, both of those are going to be continuous, and so the values can be anything between certain numbers. So, continuous process control, regulatory control, feed forward control, steady state optimization,
Regarding that fact, since we are still at the beginning,
adaptive control,
we are saying.
online search strategies. That's one I'm not familiar with. I mean, I'm familiar with online searches, but
It's proposed to have
and
So, do we have
expert systems and neural networks. Expert system, you should remember talking about that in human factors from last spring. Neural networks are particular computer networks that are made to mimic the way the brain works in a computer. And be able to answer a certain question or certain questions. And I don't want to get too deeply into that, because we don't usually require people to take neural networks here. All right, so we have regulatory controls. Our objective there is we want the performance of the process to be at a certain level or a tolerance band within that level, which is why I brought up quality control, because one of the things that we do in quality control is we are constantly measuring to make sure we're within that band.
The proposal is talking about the problem of recycling storage units of the battery.
So our performance measurement, we may compute that based on output variables.
Sorry, I lost something. Okay, going back to the
we'll often have an index of performance that we know, all right, if we're in here, we're good. Now, with regulatory control though,
self-sufficient. So,
we only initiate a control action when there's an error or we're getting close to an error. All right, so here we have an illustration of regulatory control. Oh, holy tuxedos. We have input parameters. We have our process. We have output parameters. We're measuring the variables of the output. We have our performance index measured. That's coming back to the controller, right? So the measured variables are going in, the index of performance is going in. We have a performance target level that we're shooting for, and we're going to adjust our input parameters based on that. All right, so that's
because it has.
that's not too bad.
The batteries.
Feed forward control is like feedback control, except we're trying to anticipate the effect of any disturbances
Yes.
that might upset the process. We're going to sense and compensate for them before they affect the process. Right? So kind of like a balancing act on a high wire. The guy's carrying the long pole to help keep him steady, and he sees that a bird is about to land on the end, so he compensates a little bit for that, so the bird doesn't throw him off.
Batteries.
All right, that may be a
They are
terrible
using
analogy.
hydrogen storage. That's what the proposal is saying. So, if you are using the parallel.
Usually, we're able to do this because we have a mathematical model that tells us what the disturbance, what effect the disturbance is going to have on the process. Right, so we're running a process, the pressure gets a little low on one of our input parameters. Our mathematical model says what will happen when that happens, and our feed-forward control compensates before it begins to happen.
It says.
Of course.
Draft, when you give me that Excel sheet.
Compensating for those
there's
disturbances
a hyperlinks, and in the.
can be difficult
one of the
due
lines, it says
to the
here's
fact that you have
draft.
variability.
I don't have the computer in front of me. I'm using my.
And there's likely to be imperfection in the
Maybe I
mathematical
highlight it
model
for you and send it,
and in the
by
control
email
actions.
After this.
Right? So it goes to that statistics thing where we're always worried about variation. So usually we're combining feed forward with a regulatory type control.
Sure, I will.
Usually these are used more in the process industries, right? So you remember when we were at the power plant, right, they were looking not only at what was going on all the time, but they were kind of saying, well, it looks like the temperature over here is getting a bit low. Let's make sure the system is aware and going to compensate. Now, feed-forward control can be combined with, well, you know what, let's talk about this next time. Because we have reached our magic 3:20. Are there any questions? This is your chance, Terrell. Show us you're alive.
Yes.
I'm the only one on the Zoom. All right, well, I guess that gives me an excuse to leave that. Marcy, any questions?
No. I saw that some of the dates changed for the homework. Did they? I think
What was the
homework
problem
2
for-
changed to, I think, this week.
Was the problem? is that-
Oh, I hadn't assigned homework 2, so when I assigned both of them, I actually gave you 2 weeks for both of
Next
them.
week, okay.
Because I said, you know what, it would be mean to tell these guys, oh, by the way, I didn't assign homework, but it's already due. And I'm never gonna be able to win NTU Teacher of the Year if I do that kind of stuff.
Hello? This is your cell phone! What do you...
Okay. All right. Well, have fun. I will see you on Wednesday. Oh, man. Yeah, Wednesday's gonna be a really exciting day.
Why?
Oh, I'm lying. Tomorrow's gonna be an exciting day.
Oh, okay.
Wednesday may be quite ordinary, but tomorrow I've got like 5 different things I've gotta be on. 2 of which are overlapping.
Yep.
If anything comes up, don't hesitate to come by and, and ask for help.
Okay. I'm gonna see if we can try to come back tomorrow. I'm gonna make sure I have all my stuff in order first, like homework questions.
Okay, that sounds good. I have something terrible to tell you.
Okay, since it's terrible, I have to hold the meeting. Okay?
Okay, well, you can hold, all right, it's not so terrible, you have to stop the meeting. Go ahead and meet. I'll tell you tomorrow.